Alright guys, welcome back. So today we're going to do some more antiderivatives. So we talked about what to do if you have polynomials and if you have things added together or have a constant in front. We're going to talk about some other kind of more special situations, some special integrals here. Okay, so what if we have to take the antiderivative of e to the x dx? What would that equal? Well, let's think about this, right? What this is saying is it's saying what function has a derivative of e to the x? Oh, what function does have a derivative of e to the x? It's e to the x. Cool. Okay, so that antiderivative is just e to the x plus some constant c. Okay, so e to the x is its own derivative and antiderivative. All right, well, let's look at another one. Say we have to integrate 1 over x dx. Now, you might look at this and try, okay, well, what if I wrote that as x to the negative 1? Well, I could use the formula, right? I could add to 1, negative 1 plus 1 is 0, divide by 0. Okay, now we're kind of in trouble. Like a 0 on the bottom, that's not going to work. So let's think this is a special case. So what this is really saying is, think about it, it's saying, oh, what function has a derivative of 1 over x? Do we know a function that has a derivative of 1 over x? We do. It's just the natural log of x. Okay. Now, there is also one more thing we need to take account of. We need the absolute value on this. So it needs to be natural log of absolute value of x. And the reason for the absolute value is it's still defined for negative x. Because if you try and take the natural log of a negative number, that doesn't work, but 1 over a negative number does exist. So you want to make sure your antiderivative exists as well. Okay, so that's a special antiderivative. Let's look at some other cases here. Suppose you have to take the antiderivative of x cubed minus 4 over x. Now, when we took derivatives like this in the first couple weeks of the year, one of the techniques that we use, that we're also going to use here, is to split this up. So split this up into two different terms. Break apart the fraction into x cubed over x minus 4 over x. Okay. And then from there, we can see I'm basically just taking the antiderivative of x squared minus 4 times 1 over x. Okay. And then hopefully it's not too bad. So once we split apart the fraction, this is just x cubed over 3, and then minus 4 times the natural log of x plus c. Okay. So that's how you'll actually go ahead and do that antiderivative. Okay, so that was another one. Let's look at some notation here. So just notationally, you might see something like this. You might see integral dx over x cubed, or integral dx over x. Now, what I want you to think about these, don't get confused by just seeing the dx. It's just kind of saying it's multiplied, they just combine. So they like combined the dx with the fraction. So you can really like write these as 1 over x cubed times dx and just do the normal thing. You could write this as 1 over x times dx. So when someone asks you to find, for example, the integral of dx over 3x squared, like don't get scared off by this, right? You want to write this as, okay, so it's antiderivative of 1/3 times 1 over x squared dx. Okay, so that's like 1/3 times x to the negative 2 dx. All right, so to do that, let's see. I'm going to leave the 1/3 in front. I'll raise the power bonus, so x to the negative 1 over negative 1 plus c. So I could clean that up a little as like negative 1/3 times x to the negative 1 plus c. But that's the strategy, is if you see dx over something, just kind of take that little guy and move it to the end separately. Don't get confused by that notation. Okay, let's talk about some more special antiderivatives. What about trig functions? So if we take trig antiderivatives, and basically this is just going backwards on the table that you memorized a couple weeks ago, right? About a month ago now. If you have sine, you know the derivative is cosine. If you have cosine of x, you know the derivative is negative sine of x. If you have tangent, you know the derivative is secant squared. If you have cotangent, you know the derivative is negative cosecant squared x. I can see I did not leave myself enough room. If I have secant x, I know the derivative is secant x times tangent x, and then the same thing with cosecant, but I'm out of room for that. So what that means is that if you go in the opposite direction, that's what you do for taking the antiderivative. So when you take the antiderivative of cosine x, again, it's saying what function has a derivative of cosine. So So we kind of work backwards on this table. So where do we see cosine here? Okay, so cosine is the derivative of sine. So that means the antiderivative of cosine is sine of x. Now we do need to be careful with sine. So if I ask you to integrate now sine of x, well, let's think about this. Again, this is saying what function has a derivative of sine of x. Now in my head, I'm going to say, okay, if I had cosine of x, if I took the derivative of that, that would give me negative sine x. Okay, but I don't have a negative here, right? So if I'm going backwards, I need to put in a negative. It's going to be negative cosine of x plus c. And again, in my head, I'm kind of checking my work. Okay, the derivative of this is negative sine. Okay, yeah, that works. We're good. Okay, so we're good. All right. So that's how you can get the antiderivative of that. If I give you something like, antiderivative of secant x times tangent x, you look at that and say, okay, well, what function has a derivative of secant times tangent? So you think about the trig table that's in our hearts and in our minds. Oh, secant tangent, that was the derivative of secant. So when I go backwards, when I take the antiderivative of secant tangent, I'm going to get back to the secant of x. Okay. So one more thing, if we combine some of these, right? If we take the antiderivative of, say, 3 sine of x minus secant squared x plus 4 over x squared. All right, now, of course, something like 4 over x squared, you want to write as 4x to the negative 2 right off the bat. So let's work through this. Okay, so just go part by part. Don't try and do it all at once, just go part by part. So what function has a derivative of sine? Well, not cosine, because that'd be negative sine. So that'll be negative cosine. What function has a derivative of secant squared? Tangent. Okay, and then 4x to the negative 2, so that'll be plus 4, and then x to the negative 1 over negative 1. Okay, so now we can combine these. So that's negative 3 cosine x minus tangent x, and then minus 4 times 1 over x plus some constant, c. Okay. So that's just some of the trig and e and natural log, just some of the other useful antiderivatives that we're going to be using here. The only other thing I wanted to do is this, how do I integrate, maybe not an example, but how do I integrate something like 2 to the x, or 4 to the x, or just basically the integral of a to the x, where a is a constant. Okay, now here's how you want to approach this type of problem. Let's go back and first off think about a derivative. What is the derivative of, say, 4 to the x? So you go back into the annals of history to remember what we learned a few weeks ago, and you're like, oh yeah, the derivative of 4 to the x was just 4 to the x times the natural log of 4. So you just multiplied by this constant. So what that means is that when you integrate 4 to the x, instead of multiplying by the constant, what you're going to do is the opposite of multiplying. You're going to divide by the constant. Okay. Now, my hope is that this makes sense, because if you were to check your work by taking a derivative, like if you took the derivative of this, the derivative of 4 to the x over ln 4 is leave the constant in front. The derivative of 4 to the x is 4 to the x times the natural log of 4. That base, that ln 4 cancels. That's what we want. So that's us checking that this is correct. So to generalize, right, if we take the antiderivative of a to the x, we get a to the x divided by the natural log of a plus c. So that's kind of the general formula which we'll use. All right, so that's what's going on here. Thanks for watching, guys. Bring some questions to class on these special antiderivatives.